everyone, it's Judy Warner. Thanks so much for joining us for our fourth and final day of our DesignCon tailgate party. My final guest is Daniel Beeker, who's the Technical Director at NXP. Dan works on leading and bleeding edge solutions at NXP and has decades of experience working with some of the most difficult technologies around automotive. He's going to talk about a very counterintuitive and what he says is heretical approach to EM field theory and how that has positively affected his career and his ability to be confident to pass EMC every single time. I think you're really going to enjoy this conversation. I will share the links to Dan's two talks in the show notes below, and make sure you come by and see me at 11:08. I'm looking forward to being with you next week. Meanwhile, let's jump right into this conversation with Dan Beeker of NXP. Hi, Dan. Thanks so much for joining us today. I'm so glad to see you again, my friend. It's been fun having a little reunion with you and hearing that I'm actually going to probably see you at DesignCon this year.
Yes, that's pretty exciting. In-person conferences again and meeting with all of the other engineers and the people on the trade show floor so you can see the latest and greatest technologies and products that are out there. All that is definitely something I look forward to. And more importantly, networking with my friends. So yeah, it's really good to talk to you again. And remember all the times in the past and on we go.
On we go. New chapter. Well, Dan, a lot of people know who you are, but why don't you take a minute and introduce yourself and tell us a little bit about NXP and the role you have there.
Certainly. So I'm Daniel Beeker. I've been with the Motorola Freescale NXP chain since 1980. I had my 42nd anniversary last August. I just recently was promoted to technical director, which is an exciting position to be within the company. I've been in field applications and supporting automotive since 1987. Before that, I worked in our development tools group on in-circuit emulators. So high-end computing systems where you had to be able to do emulation of a processor over a 4-foot long cable and try to get good signal integrity and fidelity for the software at what I thought was the highest level. When I moved to the automotive team in 1987, I was expecting to be going down in technology because I worked on 68020, 68030, 68040, Motorola's hottest stuff. And so when I moved to the field office, I thought, oh yeah, I'm going to be in automotive. It's old stuff. I was never so wrong in my assumptions in my life. In automotive, they're constantly pushing the edge of the technology because you're not designing with what's here today. You're designing with what's going to be here in 5 to 10 years. So wow. I found very quickly that I fell right into the leading edge of the technology. Add to that challenges of automotive, which are high volume production, and high reliability, and absolutely driven by cost. So it has to be done the cheapest, bestest, fastest, most reliable method on the universe. And that is an extreme situation where everything pushes in the opposite directions. So it's exciting and challenging. And so I've been involved in everything from advanced engine control development, electric vehicles, inverter designs, the autonomous vehicles with the radar and the LiDAR and all the other fun stuff, and then the massive amounts of computing that needs to come on the vehicles now. They're integrating full-blown network server control systems into vehicles, and that all is just a lot of fun. I've been enjoying every minute of the ride. So that's kind of where I'm at today. I just recently became a senior member of the IEEE, which is another exciting milestone within my career. And I'm working on some of the biggest, most exciting, highest performance processors that I ever have in my career. And those programs are ongoing right now. So 5-nanometer geometries, multi-core gigahertz systems with all kinds of interfaces on them, and doing the tools to support those products I manage a small skunk works where I design and develop products that NXP will sell to customers. I work with the IC design teams within the company to do everything now from working on floor planning and the ball map and the substrate design and the technology required for the debug tools and the debug hardware, and working directly with customers on their architectures for their circuit boards. So all the way from the transistors in the middle of the part down through the wiring harness, I'm being able to touch all of those. And the knowledge that I've gained, especially in the last 10 or 15 years, has really shown how important understanding the science is. And when you understand it from the perspective that I've been blessed to have, as from my association with Ralph Morrison, the rules are simple, the fields are dependable, and if you know those two things and believe them, your results are going to be extraordinary.
Well, I have so many questions for you on that subject and things that I want to tease out of you for our audience today. But first, why don't you tell us what, I know you have 2 talks this year at DesignCon, which is next week already, and tell us about what those 2 topics are and why you chose those in particular.
So the one I'm the most passionate about has to do, again, back to the basic science. And what I found working with, especially my automotive customers, so I deal routinely with billion-dollar companies, the very large OEMs, the tier ones, NXP. And the thing that I'm finding that's happening consistently throughout the industry, and it's not just automotive, it's the whole electronics industry, is that passing EMC is something that is kind of a magical event. And even the biggest companies with the large engineering teams admit that it might be 3, 4, or 5 design cycles before they pass EMC. And the worst thing is that each time they respin the board, they are not any more confident that it's going to work the second time or the third time than it did the first time. So that fell into my perspective, which I call the $1 billion mistake. Because the cost of respinning these boards is enormous. In some programs where there's a complicated board, it might cost them $30, $40, $50, or $100,000 each time they have to spin the board. And then it's trying to expedite the redesign after they failed whichever level of testing. They pay expedite fees to get a new PC board fabricated. Hopefully they have parts, because in today's environment, they may not be able to buy all the parts to do these additional spins that weren't in the original budget or time frame. And then they've got to wait, for these times while they're trying to get the board redesigned. And then they beg for time in the test chamber again and cross their fingers and pray that it's going to pass. And this is iterative rolling of the dice. They never take the time to go and look at the underlying causes. One, the fact that the skill sets are just not there. The design guidelines are not supporting the science, and they typically will blame the semiconductor vendor because it's always our fault because we have the chips that are making noise. This whole process is not engineering, and it's costing the industry. When you look at thousands of engineering teams, all well-meaning, all skilled engineers that continue to develop products that they are pretty sure are going to fail. And that's the $1 billion mistake. When you add all that up, it's probably many, many billions of dollars a year.
That's what I was going to say.
That are wasted on good teams designing products that they are pretty sure will not pass EMC. And there are no reason for doing that. If you really take time to understand why they failed or why they passed, and then use those to create the appropriate guidelines for how you develop your products, then success changes completely. Since I've started using the rules that Ralph Morrison taught me, every board that I've worked on has passed the first time. When my customers listen to me and I show them what they have done that breaks those rules, and they're really simple. This isn't rocket science. And they go make the changes according to these physics-based rules. They have a 100% success rate with customers in their redesigns. So there is no excuse to continue to make these boards that are most likely going to fail. And we need to work harder as an industry to make sure that the education is there properly, because it's not being taught the right order in school. They may teach people field physics, but it's done as a secondary level of understanding. They teach circuit theory first. Everybody gets stuck in the idea that current flows in a loop and wires carry electrons. None of that's true, and the guidelines that we use every day are based on that misconception, and that's what my class is about. To try to reconfigure and recalibrate us so that we understand the very basic laws of physics. I mean, we're not dealing with calculus and high-level math. It's very simple, easy to understand concepts that are good for both everyone from the PC board design community, which are, these guys are so skilled, they understand how to use a tool, they know how to build a board that can be fabricated and assembled. Give them guidelines that they can understand, and everything happens. Then there's magic. But right now, the idea of EMC and field behaviors as being black magic is the basis of the continued failure within our industry. So that's
Especially
my first class is going to be.
Okay, what's the actual title of the class and what day is that, Dan?
The class is, I need to check my calendar.
Well, if it's not handy, I'll find it and throw it in the show notes.
It's going to be Thursday afternoon at 2 p.m. Pacific. That class will be, that's the $1 billion mistake.
Okay.
And be there. We want to hear that stuff.
Yes.
You'll leave with a much better understanding of fields. I'll give you some resources to go chase down, and changing the simple perspective is going to be a game changer. And just the message to these design teams is, if you figure out how to do your designs so they're first time compliant before your competitors do, you win.
You win.
Your customers win, your stockholders win, your teams win. And then the other thing that is that you're no longer wasting your time trying to fix today's design. You're able to release that and go work on the next product. And that will expedite your company's process into the future, improve your market share, and you guys win. So take that to heart. Whoever
and it makes you look like a genius.
Wins. Yeah. And it makes you look smart. Even though it's really simple, just tell them, oh, yeah, it's really hard.
Yes. Tell my deep study.
That's what they told us in school, is how hard it is. It's not. They lied to us. I believed it was hard for most of my career. That the rules are simple, the technology is simple, and the results are always predictable. That's the important thing.
So
the second
for
class,
listeners, okay. Go ahead. Go ahead. I'm sorry. I think there's a lag in our audio.
The second class is an expansion on that concept. It's called PCB design techniques to improve ESD robustness. Now, this is one of the final test stages typically in qualification, certainly in automotive and in all the other marketplaces as well. And there are certain things you need to do. First, you need to understand what is ESD. The other thing is, what things can you do to mitigate these big impulses of electromagnetic field that can cause all kinds of damage on your printed circuit board and in your product, both during assembly and manufacturing, as well as once they're finally in the hands of your evil customers who do everything they can to break things. So the ideas are, again, I'm going to revisit the basic physics and the techniques that you use to manage electromagnetic fields on the printed circuit board, and talk about ways you can take care of your product from start to finish. And it's basically good transmission line design. You've heard Rick Hartley speak about this hundreds of times. Those same rules apply to improving ESD robustness, but just at a little bit higher level, because the focus is going to be on what structures can you use on your circuit board without adding cost in order to make it so they will survive at higher levels. One of the examples I talk about is a two-layer board with a quad flat pack 90 nanometer microcontroller, an LCD display, and we were able to achieve 25 kV ESD robustness on that design by managing the copper properly and taking care of all of the transmission lines in such a manner that we could make sure that the impulsive field didn't interrupt or cause damage to the behavior of the system. That was for an AC power meter. So very high reliability requirements, extreme environment, and we were able to do that.
Well, you've been sort of a mentor and teacher to me for a long time. And for our audience, Dan used to be a keynote for me at Altium Live. So we had lots of talks. And we also, because we were doing it in Europe and in the US, had lots of time to talk, friendly talk. And he would teach me. And I always remember thinking, Dan, in the industry of electronics, you're like the guy saying the emperor has no clothes, in that you're a minority, in the minority of the way. Yes, you're a heretic. Except what has been really compelling to me is how many stories you've told me about working with these multi-billion-dollar OEM companies and telling me very specific use cases in which this happened. And you've so convinced me. And also, Ralph Morrison, I know, was a dear friend and mentor for years and died a few years back. And it's a tragedy we lost him, but his books are still around. So first of all, why do you sound like a heretic today? And what is the impact, without going deep in the weeds on the story, because it's a complex story, but how did Ralph Morrison impact you and convert you in the way that you've sort of converted me over time?
Certainly. It's a long story, but I'll try to compress it as best I can. I'm a heretic because I believe in electromagnetic fields as the medium through which energy is transmitted. And taught for years and practiced by most engineering teams around the world is the idea that there's electrons moving in wires and current flows in the conductor as opposed to the electromagnetic field. The sad thing is most of the simulation tools are built around that premise. So what happened is I was working on a pre-silicon emulator for a new micro for Motorola, and one of the manager or president of the service bureau I was working with had an argument with me about implementing a specification that Motorola had called the Motorola Active Probe Interface, MAPI. And it had discrete analog grounds, and it had discrete digital grounds and discrete power grounds for the board-to-board interface. And this is Jerry Schmiel, so if you know him, he said, you don't want to do that. I said, but this is the Motorola spec. We have to do this. It's the way it's done. And he said, no, it doesn't do what you think it does, and I'm not going to do that. I said, you work for me. You're going to design it my way. I'm paying for this board. And he said, no, you're wrong. It doesn't work the way you think it is, and you need signal integrity training. I'm like, I have 25 years as a senior engineer. I know what I'm doing. He said, no, you don't. You need to get signal integrity training. It's in California. And I went, I need signal integrity training, and it's in California. So I went to my first PCB West and took Rick Hartley's 2-day signal integrity seminar. And 5 minutes into that class, I knew that every design I ever did worked by accident, not on purpose. And I remember thinking, I hope my boss doesn't figure this out, because I felt so stupid that I had been locked into this circuit theory thing. I was a dyed-in-the-wool circuit guy, digital I could hook up wires with the best of them. I could do Boolean algebra, and it didn't matter where ground was because it was just another wire. And had no idea about RF or signal integrity or fields because that was RF guys had to do with that. Power guys. I didn't do that. I'm digital. I don't care. But no. And then coming back from PCB West, after I made Rick Hartley crazy for 2 days and then longer, we were getting ready for our first Freescale Technology Forum. And that was going to be held in Orlando. My boss made the mistake of having me sit in for him on one of the days, and he was involved in the content for the day. So during a lull in the conversation, I started ranting about how we needed to provide better signal integrity support for our customers. We were at 90 nanometers then. We were moving into 55 nanometers and smaller. I said, my customers can't even design TTL without failing EMC. So what are we going to do to support them? And they said, okay, smarty, we'll give you an hour, put together a panel of experts, and let's have a chance for people to talk about it. I went, okay. So went back to my office because now I've been challenged, and I don't know any signal integrity experts. So I started pulling the books that I had on my shelf that I bought to make me look smart, like everybody else. So I had Howard Johnson's books and Lee Ritchie's books, and all of the big guns
Henry
in the industry.
Ott, Morrison.
Henry Ott. So I started calling all of them to ask them if they would come to this Freescale conference. Unfortunately, the same time that they were having the conference for us, there was a big international conference in the UK. So all these guys are going to England for this conference. And so I couldn't get any of these big guns. And one of the books I had was Ralph Morrison's Grounding and Shielding book. I called and left a message for Ralph, and he called me back and says, who are you and why are you calling me? I said, I'm Dan Beeker from Freescale, and I'd really like you to be part of my panel discussion. And so through our talk, I found out that he wasn't just an electrical engineer, he was a physicist. And, oh my gosh, you're the one. So you're my foundation guy, you're going to go first. And then I was able to get Rick and a couple other instructors from the PCB West that agreed to come to the conference because they're paying for everything. So these guys are all hot for that. Everybody talked about then how important the University of Missouri at Aurora was and their work in EMC and PC board technology. So I found out that we were actually members of the consortium. So I had a little bit of thud factor when I called them to say, hey, could I talk about getting some people? So I hit the home run there. I got Dr. Todd Hubing and Dr. Durniak both came as part of my conference. Then also I wanted to get a signal integrity expert, and I found Lee Hill, who was a graduate from UMR, who is a prominent EMC signal. He has his own company, and then one of the best known EMC and signal integrity consultants out there. And then I had another friend who was the chief technology officer for X2I capacitors. So I had this wonderful panel of experts, and Ralph went first. So Ralph talked about fields and defining where fields went, and he did his first where he's talked about halls and walls, and we'll go through that in a minute. And then it went through the progression, and as it went along, Ralph's getting more and more agitated, and Ralph's in his 70s already. So I'm seeing him kind of, I'm up the top, and he's sitting over there, and he's starting to get antsy in his chair. After the panel discussion, he walks up to me and he's jumping up and down. He said, they got it wrong. It's not how it works. And I went, Ralph, calm down. So let's go have lunch and let's talk about it. And so he started talking to me about how big a misconception there was in the management of the energy, that it wasn't current flowing in wires, that it was the electromagnetic field in the spaces. And from then on, I said, okay, Ralph, what you say makes sense. I was able to hire him to come and teach a number of seminars in Detroit for my automotive customers, as well as I brought some of these other experts in to do the same thing. But from that, Ralph decided he was going to adopt me as his apprentice, and he was going to teach me field physics or kill me trying. And so it took me more than 10 years to unlearn all the circuit theory and start to trust in geometry and spaces. And one of the most exciting moments in my career was I was doing a seminar in Austin for the applications and IC design teams were in it for Freescale at the time. And Ralph was in the audience because I was there trying to help him pitch some of his ideas to the corporation. And he walked up to the stage after the talk, and I knew he was going to chew me out for something. And he said, "Dan, I think you finally got it." And that was one of the most exciting moments of my career, and my confidence level went up significantly. But from what Ralph taught me and those techniques and the management of the spaces has resulted in my guaranteed or expected success. I don't expect to fail EMC. I expect to pass. And that's what every engineering team should be doing, is to know that you're following the rules, you're building a circuit board that makes the energy do what you want it to because you understand what it takes to control electromagnetic field. That
Well, I
was quite an
think,
adventure.
well, I've heard these stories, of course, before, but what I think is so compelling is one, that it's a physics-based science, and then two, all you sort of experts out there don't agree, but why your particular philosophy resonates with me is because what you do for a living every day, and the body of work that you've done over decades where you're like, "Oh yeah, I expect to pass." I don't know any engineer that goes into EMC and goes, "Oh yeah, I'm going to pass." It's like crossing your fingers and your toes and, "Well, I just took one more class from Todd Hubing or Ken Wyatt and I think this is the one." And but you just go in there like, "Yeah." And so that's why it's so. But how did you become, I mean, I guess, so how do you, other than tell the story over and over again,
The
how do
faith
you,
was difficult.
yeah, okay,
I
fair
was lucky
enough.
because a lot of my early work, I was able to collaborate directly with Ralph. And one of the boards that we were talking about earlier, I was asked to do a free silicon emulator for our next generation network processor. And so to do that required using a network caliber microprocessor. So it was a gigahertz processor, 28 nanometers, zero point 0.8 pitch VGA, 400 megahertz DDR4. It had an Ethernet controller, had an Ethernet switches, multiple PMICs, multiple switching power systems. It had PCIe, SerDes, RGMI-I, SGMI-I, Ethernet, CAN, PHYs, LIN PHYs, everything in the universe was on this board because this chip is a monster. But I had to put it all together from discrete hardware. And one of the things that I did, and it caused a lot of grief with the applications people, is I took 26 inductors and ferrites off of the reference design for the network processor board. And they were like, "You can't do that." And I said, yes, I can. It's my board. If it doesn't work, I'll have to redesign it. So, but based on the rules that I've learned, this is how you do it right. We built the boards to pass CMC the first time. Took $25, $30 off the bill of materials. People are buying parts that are not only not doing what they think they are, but often they're making the performance worse because they don't even implement those parts correctly. One of the issues with these filters that people think they have to use is it makes the power supply more complex because they've got isolated connections to the part. But these parts are outside the board and they want to deliver energy on the inner layers. They'll bring a via up and down. Well, you can't get 5 amps in a space that you don't identify. For a core supply, on this processor, it was 7 amps per microsecond on the 1 volt supply. So it was a huge power sucker. And if you try to take that through the board with a single via in and out, all you're doing is slowing down the energy to the part. That doesn't improve signal integrity or reduce CMC. It actually makes things worse because the depletion waves are where all the problems are. It's the the energy that's not being delivered properly to the part from the right spot, because it's all about the field's traveling in a finite amount of time to deliver the energy. So that was another thing that really helped me gain the confidence that I have to be able
Yeah.
to accept any design challenge. I can do anything from the highest power AC inverter to the fastest processor and the fastest communication buses because the rules are exactly the same. Ralph kept hammering that on me, and it was hard to accept at first, but the rules of the physics are identical whether you're working on AC power transmission lines from Boulder Dam to the most powerful network control system that you can do, the fastest processors, or the biggest motor system that you can do. All of those follow the same rules. The only thing that changes is the geometry of the system. If you need a lot of energy, you need to have a low impedance connection so that you can have the energy that you need. If you need to have very fast systems, then you need to understand the nature of the wavefront. You need to understand the nature of the power supply, and you put those together properly using the geometry. Only thing I need is algebra. It's ratiometric, and you follow the rules. You build the structures that match the behavior of the energy, and it works. It's just that simple.
Well, I know we're almost out of time, but before I let you go, I want you to repeat Ralph's things about the peoples and the holes in the walls.
Okay.
Share that with
Ralph
our
always
audience.
ended his talks. One of the most profound things he said, and it took me a long time before I really understood truly how important what he was. Now, Ralph said that I was the first person to ever listen to him, and it just is astounding that the industry ignored the person who really was doing everything in his power to try to show them the right way. And so until I was writing his eulogy, I really didn't hammer hard enough into my poor, thick skull. And then I really understood what he was trying to say. Ralph says that buildings have halls and walls. People travel through the halls, not the walls. Circuits have traces and spaces. The energy travels in the spaces, not the traces. He was saying it all along. It's all about the space. You design good transmission lines to direct the energy. It's just coplanar waveguides everywhere because the fabricators won't give us coax. But until then, you just design the railroad tracks that help direct the energy.
Well, Dan, I keep listening and learning from you. Thank you so much for coming on today. Please make
You're
time for
welcome.
me on your busy schedule. I hope we'll be able to, grab a bite or say hello sometime in our busy schedules.
Uh,
But it's been a joy
oh,
to reconnect. And thank you so much for
thank you.
sharing. And
I hope to be able
best,
to hang out at your booth. I want to hang out at your
yes,
booth when I can at DesignCon so that your listeners can come by and we can talk about it. I love that
absolutely.
because every time I talk to another engineer or a designer, I learn more every time. And I
Yes.
can
Well,
take that and improve my designs, and hopefully you walk away with more confidence in the fact that you will, instead of expecting to fail, you'll expect to pass. Easy.
pass.
First time, first time compliance.
Well, that's a good
Thank you, Judy.
message. You're welcome. And thank you for continuing to carry that torch and help other engineers. And that's what I'm passionate about doing. You're always welcome to come hang out with me. For our audience, Dan has given me a whole litany of things for you before it'll be an absolute go-to resource for you. So I'm going to share that in the show notes. So I know I say it all the time, but really go check out all of Dan's resources.
Yeah.
And then we're going to take you out on a song that his daughter wrote about. It's all about the space. His daughter wrote and sang it. And we're going to sign off and let Dan's daughter take us out with this amazing tune. Thanks for joining us this week at our DesignCon tailgate party. We'll see you next week at DesignCon. And until then, remember to
All right.
always stay connected to the ecosystem.
Because you know it's all about the space now. It's all about the space now. It's all about the space now. It's all about the space. Yeah, it's pretty clear, you don't believe it's true, but the way show where all the fields will go. Cause all the energy only moves in space. Got all the right wires in all the right places. I know your teacher said it's a conductor. You know that ain't the way. So now listen up. If you got fields are moving, you got current flow. Cause it's a moving fields that make everything go. Yeah, your teacher, she told you don't worry about the fields. They said the math that they use isn't something you wish to use. You know the circuits are better, you just gotta make them connect. So if that's what you're into, then you know what to expect. Because you know it's all about the space now. It's all about the space now. It's all about the space now. It's all about the space. I'm bringing physics, babe. Go ahead and tell me circuit functions there. No, I'm just saying, I know you'll think you're right, but I'm here to tell you physics tells us in the fields in space it's really out of sight. Yeah, I know that your teacher said the conductor holds the key, but you know that's not the way. You just gotta listen to me. You know the fields are moving, it makes all the current flow. You gotta take all this in and lose all you know. Because you know it's all about the space now. It's all about the space now. It's all about the space now. It's all about the space.